Tukey in 1977 described an orderly way of re-expressing variables using a power transformation. The transformed variable y is therefore the original variable x raised to a power. Here we use the Greek letter lambda to indicate the power to which x is raised. The Tukey ladder of powers involves setting lambda to one of the values shown. The value lambda equals 0 has no special value, since x to the 0th power equals 1, regardless of the value of x. Tukey suggests that it is convenient to simply define the transformation when lambda equals 0 to be the logarithm function rather than the constant 1. Here we see the transformations in terms of lambda. When lambda equals -2, then the transformation is to raise x to the -2nd power, which is equal to 1 divided by x squared. Recall that the transformation for a lambda of 0 is defined as the log of x. Note that if the transformation parameter lambda is negative, then the transformed variable y's direction is reversed. For example, if x is increasing, then x to the -1st power, which equals 1 divided by x, is decreasing. Since we want increasing values of x to correspond to increasing values of y, we choose to redefine the Tukey transformation to be -x to the lambda if x is less than 0. This preserves the order of the variable after transformation. The formal redefined transformations are shown here. If x takes on negative values, then special care must be taken so that the transformations make sense if possible. We generally limit ourselves to variables where x is greater than 0 to avoid these considerations. For some dependent variables, such as the number of errors, it is convenient to add 1 to x before applying the transformation. This is the modified Tukey ladder of transformations. One purpose of transforming data is to make the relationship between two variables approximately linear. The shape of the relationship between two variables is assessed for all values of lambda to see which one makes the relationship most linear. Here we see the US population plotted as a function of year for the years 1670 to 1860. The population is transformed based on the values of lambda shown. Notice how the scatter diagram smoothly morphs from concave to convex as lambda increases. Thus, intuitively, there is a unique best choice of lambda corresponding to the most linear graph. It is clear that the relationship is most linear for lambda equals 0, a logarithmic transformation. One way to make this choice objective is to use an objective function for this purpose. One approach might be to fit a straight line to the transformed points and try to minimize the residuals. However, an easier approach is based on the fact that the correlation coefficient, r, is a measure of the linearity of a scatter diagram. In particular, if the points fall on a straight line, then their correlation will be equal to 1. Here we plot the correlation coefficient of the scatter as a function of lambda. It is clear that the logarithmic transformation, lambda equals 0, is nearly optimal by this criterion. These histograms show the distribution of times in the stereograms case study as a function of lambda. Notice how the skew changes from extremely negative for lambda equals -2 to extremely positive for lambda equals +2. The raw data are represented by lambda equals 1, since raising a value to the first power does not change its value. The least skew is found for lambda equals 0, which is a log transformation. Many statistical methods, such as t-tests and the analysis of variance, assume normal distributions. Although these methods are relatively robust to violations of normality, transforming the distributions to reduce skew can markedly increase their power. As an example, the data in the stereograms case study has a very skewed distribution. A t-test of the difference between the two conditions using the raw data results in a p-value of 0.056, a value not conventionally considered significant. However, after a log transformation, lambda equals 0, that greatly reduces the skew, The p-value is 0.023, which is conventionally considered significant.